So the next recording has started, and we have 14 students right now. And let's go back to the slides. Yeah. So we have done question 3, question 2, question 1 we did last time, question 5, question 4 we did last time, question 5 maybe we haven't done. So I think some of you have done, I know that, but others please do. It's a simple computation using your 412. Z equal to 0 is a pole. You tell me of what order and what is the residue. Okay, so I'll ask you on WhatsApp. Now what is remaining in today's class? We have to prove local Cauchy theorem, CIF and Moreira. I will go a bit quickly because we have taken more time than expected for the break. So bit quickly. So first we look at so local Cauchy theorem is Cauchy's theorem in any convex set. But as preliminary, we are going to do a very particular case, very beautiful idea. We are going to look at Cauchy's theorem for a triangle. Okay, so you can take any open set and you take a triangle inside that open set, and suppose f is holomorphic on that triangle, on the boundary on that triangle, then we want on that omega, then we want to say that on the boundary of the triangle the integral of f is 0. Okay, this is what we have to prove. We are going to formulate it as in Rudin a bit more precisely, a slightly stronger version than what I just said verbally, and this will be very useful. Okay, so this is a precise statement. You have an open set omega and a closed triangle, meaning the closed thing, all the interior part and the boundary, everything is included, closed triangle in omega, and assume f is continuous throughout omega. And verbally I said f is holomorphic throughout, but I'm not assuming holomorphic throughout. I am assuming only holomorphic throughout except at one point. Okay, so this is a formulation which is going to be useful later. Of course, it follows from this that it's holomorphic everywhere. That's another matter. But under this assumption, we want to have a proof. So this is a stronger statement, right? You're not assuming holomorphicity everywhere. You are assuming holomorphicity everywhere except at one point. And continuity you are assuming everywhere. Under these assumptions, you're going to show that on the boundary of the triangle if you integrate. So boundary of the triangle if you integrate, meaning integrate along this line segment plus integral along this line segment plus integral along the third line segment. This is 0. So this is the first Cauchy's theorem on a triangle. As a corollary, you will prove Cauchy's theorem in any convex open set, but no condition on gamma. Here there is no condition on omega, but your gamma is a triangle, the boundary of a triangle. As a corollary, you will assume that omega is convex open, but there will be no condition on gamma. That is called the local Cauchy theorem. Then we will prove a Cauchy theorem without any condition on omega or gamma. I mean, there may be some condition, but not this kind of very strict condition. That will be the global Cauchy theorem. That's a bit later. So this is the integral that you want to compute, and you want to show that this integral is 0. So I am naming it j, and we want to show that j equal to 0. So in order to show j equal to 0, we will show that the value of j, absolute value of j, can be made arbitrarily small. That's the meaning of saying j is 0. And remember that the proof has 3 cases. What are the 3 cases? So there is a point, right? There is a point on which we don't know that it is holomorphic. There are 3 cases based on this point P. Case 1 is P is the point P where you don't have differentiability given, holomorphicity given, holomorphic everywhere except at this point, meaning in a neighborhood of P you don't have differentiability throughout. At P you don't have differentiability. So case 1 is P is outside delta, it's outside this closed triangle. Case 2 is P is a vertex of this closed triangle, and case 3 is the remaining case, P is an arbitrary point of the triangle. In all these 3 cases, we are going to show that j is 0. Okay. Before coming to the slides, in fact, it will be better if you look at the book and read the proof. It's very nicely written there. The very basic idea, let me try to say verbally. before coming to the slides, bit quickly because it's already 10:37. Assume we are in case 1. P is outside your triangle. So you have this triangle and P is a point outside. And J is this integral along the line segment 1 plus line segment 2 plus line segment 3. P is somewhere outside. Okay, so P doesn't matter for now. What you're going to do is, on all these three sides, you take the midpoint and join these midpoints and form another triangle. So how many sub-triangles are there now? You're taking all these midpoints and joining and you form this triangle. So now you have 4 triangles, right? This inside triangle, and that cuts out 1, 2, 3 other triangles. So you have 4 triangles. What will be the integral J, which is on the boundary of the bigger triangle? It will be integral along one small triangle plus integral along one more plus integral along one more plus integral along one more, right? By cancellations. Inside the edge inside this bigger triangle will have one orientation and the other orientation it will get cancelled. So finally, J is nothing but the integral on the boundary of all these 4 triangles. Okay, you're with me on this? So case 1, partition this into 4 triangles, and J is the sum of 4 integrals on each on the boundary of a subtriangle. Next claim is one of these integrals. So now you have 4 integrals. J is the sum of 4 integrals. One of these integrals should have absolute value bigger than or equal to mod J by 4. You see this? That's obvious. Why? Because suppose each of this integral has absolute value strictly less than mod J by 4, then the original integral will have absolute value strictly less than mod J. That is not true. Therefore, one of these should have absolute value not strictly, bigger than or equal to mod J by 4. At least one of these triangles. Choose one such triangle and call it delta 1. Okay. Now you repeat this process. By the way, let me ask you quickly, if L is the length of the original triangle, the boundary of the original triangle, what will be the length of boundary of delta 1? Can someone tell me very quickly? Just to see whether you have understood the picture. You have the bigger triangle, you have taken the midpoints and made this triangle, and you have 4 triangles. Each of these 4 triangles, the boundary, what will be the length?
L by 2.
L by 2, correct.
Yeah.
So it's basic geometry from school. You can check, you can argue using similarity or congruence or one such thing that it will be L by 2, and this we are going to use. So you have got this delta 1, right? Delta 1 is one of those triangles. There is at least one of those where the absolute value of the integral is bigger than or equal to mod J by 4. So pick this delta 1 and repeat this process. So you will get a delta 2. Delta 2 will have length, boundary will have length L by 4, and the absolute value of the integral there will be bigger than or equal to mod J by 16. Mod J by 4 by 4, mod J by 16. So continue this process to get a sequence of triangles, one containing the other, nested triangles with the property that the length of the boundary of delta n by what you have done is L by 2 power n, and mod J is less than or equal to 4 power n times the modulus of the integral on the boundary of delta n. Right? Each process you will get mod J by 4, mod J by 16, etc. This integral will be bigger than or equal to mod J by 4 power n. So you get this. Okay, this you will get. Now observe that this nested triangles, this intersection of all these nested triangles together will be a singleton. The nested intersection will be non-empty because of compactness, right? Finite intersection property or whatever. So nested intersection will be non-empty, and it will be a singleton because the length, it's decreasing. No, the length is going to 0. So it's decreasing. So more than one point cannot be in the intersection. So it will be a singleton. Doesn't matter to us. We want just at least one point, but it's actually a singleton. And this singleton point Z0 is in your delta, again by compactness. Delta contains this point. So you have got a Z0 in delta. Now we are going to argue using this Z0 that we have got with this construction. It's a beautiful argument. This is the observation. F is differentiable at Z0. Can you quickly tell me why? Remember, we are in case 1.
Because P is outside delta,
Right.
so
P is
Z0
the
is not
only
P.
point, absolutely. P is the only point where differentiability was questionable. Maybe we don't know it is differentiable, but P is outside delta and Z0 is inside delta, therefore F is differentiable at Z0. Okay? So differentiability at Z0 you write down in terms of epsilon and delta. I have called R here. So for every epsilon there is an R such that mod Z minus Z0 less than R implies mod Fz minus Fz0 by Z minus Z0 minus F prime Z0. That modulus is less than epsilon. We have rewritten it like this. So given an epsilon there is an R such that this happens as differentiability of F at the point Z0. Okay. Now choose an n such that L by 2 power n is going to 0, right? So choose an n such that L by 2 power n is less than this R. So that mod z minus z naught is less than or equal to L by 2 power n for all z in delta n. This is okay, no? Because choose a very small triangle delta n so that if you take any z in delta n, z naught belongs to all the delta n's. So z and z naught both are in delta n and the difference will be less than the boundary of the triangle. No, these are 2 points from the triangle, closed triangle. The difference between the distance between those two will be less than the boundary, which is much bigger, and the boundary itself is L by 2 power n. So if you choose n like that, n such that L by 2 power n is less than R, then you are getting mod z minus z naught is less than or equal to the length of the boundary, which is less than R. Sorry, which is less than R for all z in delta power n. So on this triangle, if you integrate what is happening, sorry, on this boundary of on the boundary of this triangle, if you integrate fz dz, uh, what is happening? This integral is same as I have subtracted many terms, but all these terms are 0, right? Integral fz naught dz is fz naught is a constant and integral dz is 0 because it's on a closed path. Similarly, integral f prime z naught z dz is f prime z naught is a constant and integral z dz is also 0 because it's on a closed path. And the next thing is again a constant. So what I have subtracted is some number of zeros. So fz dz is same as integral of this one, and this one is less than or equal to the absolute value. Yeah, so I should have written the absolute value here. There's a typo. The absolute value of this integral is less than or equal to, no, this integral is this integral, and the absolute value of this integral is less than or equal to epsilon times L by 2 power n square. Why is that? Because if mod z minus z naught on delta n you have mod z minus z naught is less than or equal to L by 2 power n. And when mod z minus z naught is less than L by 2 power n, which is less than R, you are getting this modulus is less than or equal to epsilon mod z minus z naught. So you are getting epsilon times L by 2 power n times the length of the boundary, which is another L by 2 power n. Okay, so there's a typo here which I will correct, which is less than or equal to epsilon L by 2 power n whole square. So what you are getting as mod j is less than or equal to epsilon times L square. Why is that? Because modulus of j is less than or equal to 4 power n times modulus of this. 4 power n times modulus of this. And this is less than epsilon times something, so the whole thing is less than epsilon times something, and therefore this can be made arbitrarily small, therefore j is 0 in case 1. Clear? Case 2, P is a vertex. So here what you do is, suppose the vertices of the triangle are P, B and C. P is a vertex, right? So take P and the other two vertices you name B and C. What you do is, so first of all, if these so triangle can be collinear also, that's a degenerate triangle, in which case it's obvious. For any continuous function J is 0 because of cancellation. So suppose it's a proper triangle, it's the non-degenerate case, not collinear. Then what you do is you have this vertex P and you form 3 subtriangles. What you do is take the vertex P and on PB you take a point X, and on PC you take a point Y, and you form the triangle PXY, and also then you have X, Y, B and C join, let us say, X with that thing and form two more triangles. So you form a small triangle PXY, and the remaining part, which is like a rectangular shape, not rectangle, I mean some four sides, you join two more points and form it, cut it into two triangles. So you have three triangles, three sub-triangles. And on the full triangle, the integral will be integral on the three sub-triangles. Now I'm going to say that the integral on the full triangle is equal to integral on the boundary of the small triangle. Why is that? So you have three triangles, the vertex P and X and Y. That's a small triangle because I will choose X and Y very near to P. Then you have these two slightly bigger triangles, and the whole integral is sum of these three integrals. And I am saying that the other two integrals are zero. Why is that? Someone tell me very quickly.
By case 1.
By case 1, because P is outside those two triangles, because P is the vertex here. So by case 1, the other two are 0. So it is this thing. Now what you can do is this small triangle can be made smaller and smaller and smaller. Bring X and Y nearer to P. So integral over this triangle will be, modulus will be less than or equal to F is bounded, right? Because it's a continuous function on a compact set. So F is bounded, and as the distance, as the length of the boundary decreases, and because F is bounded, modulus of J can be made arbitrarily small again, and that finishes case 2. Okay. Case 3 follows from case 2. Why? Because what is case 3? P is an arbitrary point of the triangle. If P is a vertex, we have already done. So arbitrary point of the triangle and not a vertex, meaning what? It is a point on the triangle. If it is on one of the sides, again collinearity, no problem. I mean, in case 2, it follows. If it's a point inside, okay, so inside and collinear, I mean, no need to argue separately. If P is an arbitrary point, what you do is you form the three triangles using that P. So if A, B, C are the vertices, you form APB, APC and BPC. You form these three triangles, and each of these three triangles, the integral is 0 by case 2. Therefore, case 3 follows. Okay, so maybe this was a bit quick. If you have questions, we will discuss in the next class, or you ask me on WhatsApp. Because very quickly, let's cover the slides. Okay, so local Cauchy theorem is something you have done in multivariate, I mean in calculus long back. Very quickly, so path gamma is any closed path in omega, not just the boundary of a triangle. But on the other hand, my omega is not just any open set. I am going to take convex open set. You will see the convexity in the proof. Unlike any open set earlier, the function f is as earlier. So what is the condition? What are the conditions on f? F is continuous throughout omega, and f is holomorphic everywhere except at one point p. This condition is there. F is continuous on omega and holomorphic except at one point. Then the claim is f as an antiderivative, f as a primitive, antiderivative capital F. There is a capital F which is holomorphic throughout omega such that f is f prime. If you have this, then of course it follows that the integral of fz dz is 0, right? Because if f is capital F prime, then integral gamma fz dz is integral gamma capital F prime z dz. But integral of capital F prime is 0 follows from fundamental theorem of calculus. Just, parameterize using an interval and see what that integral is. One variable calculus will tell you that that is 0. So you just need to show that there is an f prime. That's all that you need. There is a capital F whose derivative is this f. That's all that you need to show. And that's very easy because of this triangle theorem. Fix a point A in omega, and you need a candidate, right? You need to give a candidate as an antiderivative. You need to get a candidate for antiderivative, and then you show that it's actually an antiderivative. If you get a candidate, you can show fz minus fz naught by z minus z naught and take the limit. So the candidate is, you take a point z and define capital F to be integral f psi d psi on the curve, which is a straight line joining A and Z. Why do you have a straight line joining A and Z? Because you are in a convex domain. So any 2 points can be connected by a straight line. So this is your candidate. And now consider f of z minus f of z naught. So f of z minus f of z naught will be integral on a to z minus integral on a to z naught. But that is nothing but the integral on z naught to z. Why? Because you can argue on using the triangle Cauchy theorem on the triangle connecting a z and z naught. In the correct orientation, the integral is 0. Therefore, if you subtract these two, you will get it is integral on the line segment z0 to z f psi d psi, and that's it. So for z naught equal to z naught, you can take the quotient fz minus fz naught by z minus z naught minus fz naught. This limit is what you are interested in order to find the derivative. But this is 1 by z minus z naught f psi d psi minus fz naught d psi, and f is continuous throughout. Therefore, if mod z minus z naught is less than delta, then in particular mod f psi minus fz naught, if mod z minus z naught is less than delta, then mod xi minus z naught is also less than delta, and mod f psi minus fz naught will be less than epsilon by the continuity of f. Therefore, this one is this can be made arbitrarily small. As z goes to z naught, this can be made arbitrarily small. That means f prime at z naught is z naught. So that shows that f prime equal to f by the continuity of f, and therefore by the fundamental theorem of calculus from one variable calculus, you get that the integral of f is 0. So this is what is called the local Cauchy theorem. And I'll just take one extra minute. Convex on a convex set Cauchy integral formula is now a triviality. It's a corollary to this, because this is what you have to show. This is Cauchy integral formula. Fz times a winding number is nothing but 1 by 2 pi I integral over gamma f psi d psi by psi minus z. And this follows. Proof is one line. You just consider this function. G psi equal to define like this when psi not equal to z, and f prime z if psi equal to z. This function has the property that it is continuous everywhere, continuous throughout omega, and it is differentiable everywhere except at this point z. At this point also maybe, I don't know, I don't care. So this is your p. If you take p to be z, except at this point it's holomorphic, and it is continuous everywhere. So you can apply the local Cauchy theorem to G, and integral G over gamma is 0. But integral G over gamma is 0 means this equal to this by the definition of the winding number. That's it. So a corollary to this will be, for any open set omega, every f is representable by power series. This we have already indicated in the last lecture. Once you get Cauchy formula like this by our general result, by taking the measure to be f of gamma t, gamma prime dt, etc., and gamma to be a circle, right? I mean, representable meaning given a disk you have to show. So given a disk, you can take the boundary of that disk. There's a one subtle point which you look at the book, which is also easy, and via that argument you can show that f is representable by power series, and a corollary to that is, if f is in h omega, f prime is also in h omega, because f is representable by power series, and power series you can differentiate term by term. Therefore f prime is also representable by power series, therefore f prime is differentiable, and f prime is in h omega. One more minute and we will finish Moreira's theorem. If f is a continuous function on open set, such that on every triangle in your set, on the boundary if the integral is 0, then you can conclude that f is holomorphic. Okay, for every closed triangle on the boundary if the integral is 0, then f is actually holomorphic. Proof is very easy. What you need to do is take a convex open set. Now this condition that is given to you, see earlier how did you show that antiderivative exists? By integrating on a line segment, and that was well defined. And you could do the subtraction and the differentiation argument because of Cauchy's theorem on a triangle. But that is this condition that is given to you. So by this condition given to you, you can do the same proof. You can take the antiderivative candidate and show that it is an antiderivative. You can construct capital F on this convex open set V as earlier by making use of the integral on the boundary of any triangle being 0, and since f is in h omega, right? This f in h omega, hv follows by this construction. It's an antiderivative that you have constructed, and that is in holomorphic. That is holomorphic, and therefore it follows that f small f is also holomorphic because of this corollary. If a function is holomorphic, its derivative is also holomorphic. So capital F is holomorphic by the previous construction, and small f is nothing but you have constructed the antiderivative. So its derivative is the small f, and because capital F is holomorphic, small f is also holomorphic, because if a function is holomorphic, its derivative is also holomorphic. So that shows that f is holomorphic on V, and this you can repeat for any convex open set V. So it is holomorphic throughout omega, right? F is a function on omega. You take any convex open set V, you have shown that f is holomorphic on V. And this is true for any V, which means f is holomorphic on omega. So this is Moreira's theorem. Maybe I was a bit too fast in the last 2-3 slides, but this is recalling things which you have done in 412. So most likely it's okay because you have already seen this. But otherwise, if you have questions, anyway, we recall whatever we have done in the very next lecture. But even otherwise, you can ask me over email or Moodle or WhatsApp or during the next lecture. Okay. So I think I have exceeded time by 3-4 minutes. Sorry for that. We will stop here, and let me stop the recording.
We still do have a minute left.
It's 10:55, Aryaman, actually.